now we will take a look at what do we actually do with those matrices Hamiltonians in spin dynamics. I will give you an overview first of the next perhaps 5 or 6 lectures. There are 2 categories of simulations that all of you will be doing. Very broadly speaking, they can be separated into time domain simulations and frequency domain ones. And time domain, we have our initial condition, we have our Hamiltonian, and we just evolve the system forward in time and look at the various observables in that. And this really is what describes most real-life NMR and EPR experiments. Because this is what the spectrometer actually does. It hits the system with a pulse, and then it watches it evolve, hits it with another pulse perhaps, but we're looking at time domain processes. Relaxation and such like. And so most of the real things are going on here. If you are clever, this scales really well with the system size as well. Not exponentially, it doesn't have to. And you can put in relaxation theory, kinetics, dynamics, whatever it is that goes on here. Now frequency domain simulation, as we'll see, involve writing down the Hamiltonian, looking at its eigenvectors and eigenvalues, what are the energy levels of the system, what are the allowed transitions between those energy levels. And this is the kind of formalism that is in some sense equivalent to giving the system an infinite amount of time to evolve, settle down, and then you can speak about the energy levels. Because if you don't give it an infinite time, then the energy-time uncertainty relation would mean that you can't actually specify energies accurately. And so these are those energy level diagrams that you get in the textbooks. It's only really useful for fairly simplified experiment models, because in real life you cannot just flip the populations of the 2 energy levels. It always has some time domain contributions that the equipment executes. For scaling, this involves diagonalization. And as many of you know, the eigenvectors of sparse matrices are usually dense. And so if you have a very large matrix, there's no saving grace to say that it's sparse. You will have to have dense matrices to stop. And really, it probably is an overstatement to say that this formalism is limited to coherent phenomena, but it is quite difficult to include relaxation into here or kinetics, because those are very essentially time domain processes. And so treating them in the frequency domain is, for that reason, rather difficult, although you can sort of do it. So for both, we will have, and in this course at least, we will consider 3 different formalisms. One is just the Schrodinger's equation. Yeah, we take a quantum system, we solve the Schrodinger equation, but it's got a downside in that it has to be a single quantum system. Schrodinger's equation is not adapted to treating multiple systems because you double the system size and the calculation size in squares, and even a system of 3 molecules would be difficult, but we've got 10 to the 23 molecules in the sample, and so it is necessary in most cases to treat an ensemble of systems. And ensemble is something that the density matrix makes an appearance in, so if I just say formalism, then we can either use the SE, the Schrodinger's equation, or we can use the density operator formalism. That will be the topic of tomorrow's lecture, or next week's lecture. So density operator formalism, and that is well adapted to describing ensembles. We will only be dealing with Schrodinger's equation in this lecture, so this is looking into the future. But even the density operator formalism, even though it's okay at describing ensembles, omits some of the more sophisticated types of dynamics in this system, like complicated cross correlations, chemical kinetics, and such like. And for that, we use the state vector formalism. It's not really an abbreviation that people typically use, SVF, but this is known in the trade without particular justification, really, as Hilbert space. and this is known as Liouville space. The great upside of Liouville space is the formalism is in principle complete. Anything that can possibly go on within the spin system can be accommodated in the Liouville equation formalism. However, as every general theory out there, it is very difficult to compute because the matrix dimensions of the Liouville space are the square of the matrix dimension of the Hilbert space, and the Hilbert space itself is a bit of a complication based on the standard Schrodinger's equation solution for just a single system, because in a single system we'll just have a single wave function vector. In the density operator we've got a matrix, and in the Liouville space we actually have supermatrices in there. So the complexity grows, but so does the generality. Now let's start with the Schrodinger equation then, and over the next few lectures just work our way down this diagram. And let me start from explaining why Schrodinger's equation isn't good for describing ensembles. If we have a wave function that our system is in, it would be a function of some coordinates and it would be a function of time. But what you also know exists in every wave function is that arbitrary phase multiplier in front. Now, the reason why it's arbitrary is that it doesn't actually affect the observables. So if we were to compute some observable, let's call it O, then it will be psi times the corresponding operator times psi. You see, we have an operator which is Hermitian, it has real eigenvalues. We have psi and we have psi conjugate. So if we put the phase factor out in front, we will have its conjugate, so it will be minus I phi. We will have itself plus I phi, and then we will have that bracket in there with the wave functions that don't have a phase multiplier. You see, this is, sorry, this should be, this is equal to 1. So the phase does not affect the observables. However, if you look at ensemble average of the wave function itself that gives the various distributions is the same between different molecules in the ensemble, but the phase factor doesn't have to be. In principle, the phase is random. So what we will have is EI phi, ensemble average, psi T R. What is the ensemble average of this with a random angle phi? 0. Yeah, so this averages to 0. And so the ensemble average of the wave function is 0. Whereas the ensemble average of observables and the density matrix, as we shall see in the next lecture, is not in fact 0. And so when we get to ensembles, it will be necessary to use a more sophisticated formalism than this. But for now, we will consider a single quantum system. And for that, we can actually use the Schrodinger's equation. Well, as you know, what that is d by dt psi is minus I h psi. And we'll do it in 2 stages. We will first assume that the Hamiltonian is time independent and run through the solution. And then we will lift this assumption. We will have the full time dependent Hamiltonian and show that the solution has a similar form except for one extra mathematics that we can have. So how do you solve this if this is a function and that is an operator? Well, what we can do is we can try and expand our psi as Taylor series. Yeah, it will be psi at 0, so we will expand it around 0, plus the second term in the Taylor series, d psi of t by dt at t equals 0 times t. We have the second term of the Taylor series, plus d2 psi of t by dt squared at t equals 0, a half of it, t squared, and so on. Now, curiously, we actually know what these derivatives are. because we can just plug them in from the Schrodinger's equation. If the Hamiltonian is time independent by our assumptions, then we can also compute the second derivatives of this. So the d2 by dt squared will be minus IH d by dt psi. We can plug it back into itself, and so we actually know the expressions for these things. So if I plug it in, then what we will get is psi of 0. Then replacing this with the Schrodinger's equation and putting time to 0, what we are getting is plus minus I h t, yeah, we've got the t here, psi 0, plus the second term, a half minus I h t squared psi 0, yeah, so we plug the Schrodinger equation derivative into there, and so on. Well, we've got psi 0 everywhere, why don't we take it out of the bracket? When we do that, what we'll get is a sum, which is infinite, from n0 to infinity, minus I h t to the nth over n factorial psi 0. Now, this is a series of the following general type. From n to infinity, n0 to infinity, x to the n over n factorial. Who remembers what this sums into? Exponential. So this here is the definition of the operator exponential. It's a series like that in its various powers. So x minus I h t applied to psi 0. I should wipe this out so it doesn't interfere. There we are. So here is the general solution to the Schrodinger's equation in the situation where the Hamiltonian is time independent. If the Hamiltonian is time dependent, things get, as we shall see in a moment, quite a little bit harder. And really, as all general solutions, this is deceptively simple and in practice utterly incomputable. Because if you take a classical case of a couple of atoms, the number of possible excited states they've got is actually infinite. So the matrix in question here will be infinite dimensional. Even if you cut it somewhere reasonable, it will still have dimensions of several thousands, maybe several millions, and maybe more. And so even storing it, let alone exponentiating it, is oftentimes not an option. And Dima will tell you a lot more about that. He's actually looking at ways of generating and storing compact representations of these things. So there goes. So it's actually quite simple. This is the initial condition. Yeah, this is where the system starts from. This is the Hamiltonian, and we've spent the last couple of lectures discussing the Hamiltonian, so you know what it is. And then the solution at any point in time is just this. You tell MATLAB to compute the matrix exponential for you, multiply it into a vector, that's it, you're done. And then whatever observable you actually have, you take this product and you get that observable. So all of it, so far, so good. Right, let us now look at the case where the Hamiltonian is time dependent. It will be hard because, you see, in here, the derivatives of the Hamiltonian with respect to time would now also appear, and we will have to deal with them. So what we will do, we will not actually use the Taylor series procedure, because if this starts depending on time, then there will be the product rule, and there will be multiple nested product rules, and it really very quickly degenerates into a big algebraic mess. So what we will do instead of differentiating, we will actually integrate and resubstitute, and as we will see in a moment, that also provides a solution after a fashion. So d psi of t by dt is minus I h of t, Hamiltonian is time dependent, psi of t. Okay, why don't we integrate this from 0 to t, just both sides of it? Yeah, they're equal, so the corresponding definite integrals ought to be equal as well. So if I do that, so I just integrate this from 0 to t, stick a prime for the integration variable, dt prime, and then integrate this from 0 to t, t prime, dt prime. That still should hold. Okay, so the integral of a derivative is the function itself, so we will have psi at the upper limit minus psi at the lower limit. So that is psi of t minus psi of 0 equals this thing, and we can't say anything about it. Yeah, it's just there, it's the integral. Nothing else to be said. We don't know what is h, we don't know what is psi. We can only formally write the integral down. So that will be minus I integral from 0 to t h of t prime. I'm just omitting these hats at random. Every operator should have a hat. Well, it has in your handout, but please bear with me. On the board, t prime psi t prime dt prime. Or I think I'm calling it t1 in the handout. Actually, equation 6, the rightmost term, h should be of t1, the integration variable. Equivalently, what we can do is move psi 0 into here. And so finally, what we will have is an equation that is, on the one hand, formally equivalent to Schrodinger's. We didn't make any approximations or assumptions, we just integrated it once. But on the other hand, doesn't get us anywhere closer to the actual solution, because the only thing we did is to integrate both sides formally, and we still don't know what the solutions are. So that will be psi 0 plus the integral minus I from 0 to t h of t1 psi of t1 dt1. Right, but what we now have is an expression for psi in terms of itself. Why don't we go back to our original Schrodinger's equation here and plug psi into here? So what we will have then is the derivative of the psi will be minus IH times that crocodile, and we'll integrate it again. It's not immediately obvious why we are doing that, but after we've done a few steps, you'll see what I mean. So the basic stages are: take the Schrodinger, integrate, plug into itself, integrate again, plug into itself, integrate again, and so on. So once we've done that process, what we'll see is this: psi t will be equal to the following operator: 1 plus minus I integral from 0 to t dt1 h1 h of t1, and this is an integration operator. Yeah, I'm writing it in an integral operator notation. So it acts on a function, then multiplies it by the Hamiltonian and integrates the result. It's used in that sense. Plus minus I squared integral from 0 to t dt1 integral from 0 to t1 dt2 h of t1 h of t2 and so on, applied curiously to psi 0, the initial condition, which comes out of here. Okay, so this is still formally equivalent to the Schrodinger's equation. We've just done this multiple integration and resubstitution process. What we can rewrite it in terms of is matrices. So it will be a sum from n0 to infinity. You see, I'm starting to build something vaguely resembling Taylor series, but it's not yet a Taylor series of some operators. I'll call them un of t applied to psi 0. So we sort of got it into the shape that we got it in here. yeah, we had this psi 0, we had this operator which turned out to be an exponential, but we've got something here that's manifestly not an exponential. There's a big bunch of integrals in there. Whereas the expressions for un, it's just n-fold sequential integral with these Hamiltonians in there. Well, why don't we take a look at it and see if we can do anything about it? So un is z-carry integral, so it's minus I to the power n integral from 0 to t, dt1, integral from 0 to t1, dt2, and so on, integral from 0 to tn minus 1, h of t1, h of t2, and so on, h of tn. And that's an operator. You see, it's a so-called chain integral, yeah? The next integration variable depends on the upper limit of the previous integral. That makes it very awkward to compute. However, what would make it less awkward to compute is a theorem which I've stated without proof in equation 8, which says that for a function that's totally symmetric with respect to all of its arguments, we can actually transform this integral from a chained integral to an integral over independent parameters. For that, we need our Hamiltonian to be totally symmetric. This product to be totally symmetric with respect to all of these times. The times are naturally ordered. Yeah? If you look at the integrals, then the times are ordered in a sense that Tn has to be smaller than the Tn minus 1. It just comes out of this process. So the only way we can use that theorem is if we keep this product always ordered like that. So why don't we introduce an operator that would always keep it ordered? So we'll introduce a very interesting thing. We'll call it T. It will be a super operator because it acts on operators. And its job would be, when you feed it this expression, would be to examine the order of times and to swap them around so as to always keep that order ascending. That would satisfy these equations on the one hand, because we always have the order ascending, but on the other it will satisfy the theorem in equation 8, which will allow us to unchain these integrals. So it's a bit of a subtle argument, but there we are. So after we've applied that, and I've done the full derivation in equation 9, but I will just spell out the result on the board, we get 1 over n factorial, and you can see we are starting to get even more chunks of a matrix exponential out. Then there will be this ordering superoperator. And really, because the integral in equation 8 became an integral in the limits that do not depend on each other, we simply have a single integral to the power n here. So minus I integral 0 to t h of t prime dt prime. So quite simple, to the power n. And the reason why we could do that simplification is the presence of this so-called time ordering operator, whose job it is to maintain the time order, so we could apply the transformation. Okay, so what we now have, finally, once we put everything together, and it's a bit of a derivation as you can see, it's a t superoperator, then in brackets we've got a sum from n0 to infinity 1 over n factorial minus I integral from 0 to t h of t prime dt prime power n applied to psi 0. Well, that's a Taylor series. It's 1 over n factorial over something to the power of n. So it's in fact an exponential of this integral. So what we finally have is this expression that all textbooks give, but no textbook ever explains. Time ordering superoperator, exponential minus I0 to t, h of t prime t prime applied to the initial condition. And this is the time-dependent equivalent of the solution that we've got here. Now, the practicalities of computing a time-ordered exponential are such that even in the simplest cases, it's basically incomputable. So it's easy to compute the exponential of just a static matrix, but the fact that you've got this time order in front and that it properly acts on these expansions would mean that you'd have to have all of these expansions and actually apply the time order and so on. So in reality, the practical way of computing solutions involving time-dependent Hamiltonians is to assume the Hamiltonian to be piecewise constant. So if this is a parameter of your Hamiltonian and it varies in a smooth way, then what we can say is, why don't we cut it up into little pieces? Assume that it's approximately static at each piece, which would be a pretty decent approximation if we choose this splitting to be fine enough. And then just use the time-independent equation in every case. So on your first slice, the Hamiltonian will be equal to something, but it will be static. Exponentiated, t will be the size of that slice, propagates the system forward by one step. In the second slice, the Hamiltonian would be different, so the exponential would have to be recomputed. The initial condition will be the result of the previous calculation, propagated forward by one step. Next step, and so on. So this sequential application of matrix exponentials that you all have seen by now many, many times is in fact a discretization of this expression here, because the original expression, except in the very trivial analytical cases, is in fact very hard to compute.
Can you comment on this question once more? It looks for me that after we take the exponential, it has only one variable t. So it's not obvious what the
we took this out because it's a linear operator. So this is a symbol.
Okay.
So I guess a simple analogy would be to say that sin h is a hyperbolic sign, not a sign times the variable h.
Okay, so it's not about computing the exponential or the integral.
No, it's an actual function called a time-ordered exponential. Perhaps a better way of writing it down would be to say this, xo of something. This is the notation I'm using in my papers. So to say that this, in fact, is a different operation from the exponential. It's an exponential that's been computed. So this
and one more question. When we define the t operator, which acts on n of on un, it sorts n operators.
That's right.
But in different term, it sorts, say,
A different
n
number.
plus 1 operators. So it's not obvious how you can take this out of brackets, because the operators are actually different operators.
It won't have a representation. So it is taken as a notion. So it's a more general prescription than just a map on a space of operators. It is a map that has been defined to adapt itself to the number of operators that it's acting on. So you can see why computing a time-ordered exponential is in practice not an option.
Yes, but if we define this way, we cannot be sure that it's linear. So we cannot take it out of brackets, because it is adaptive to n.
It is.
So why should it be linear after it adapts?
It's linear for each n.
Yes, but you cannot then
as
take
you
it out of brackets, because there are different operators for each n.
Correct, but if you define it not as a map between any fixed spaces, but as a map in a more general sense, I suspect mathematicians would find that blasphemous, but physicists generally don't worry about these things. So, okay, let me just put it that way. In any practical calculation whatsoever, what everybody's doing is this. So just treating a problem as a sequence of constant time problems, and there it's all understood. It's just this T symbol, Dyson operator, makes an appearance far too often. And far too often when I start poking people about what it is that they meant when they put it in there, they don't actually know. So now you guys, when you get to your examination in magnetic resonance in the end, you've got no excuse. Because I'm totally wrong. Okay, so, right, so these are the ways of solving the Schrodinger's equation in the time domain. And as I said, practical calculation is just a product of matrix exponentials with fixed Hamiltonians. It's not very clear how much time we would be able to squeeze. What I've got in the handout is an example of how to solve a very simple problem, just a single spin, with this matrix exponential. So equation 14 defines a Hamiltonian, which is just the Hamiltonian of a simple Zeeman interaction, where you have a single spin in a magnetic field that is directed along the z-axis, and we simply have an interaction of a magnetic dipole with the applied field. So it's omega sz, where omega is the Zeeman frequency and sz is the Z Pauli matrix. So what we then do is we just go ahead and honestly compute the matrix exponential, and I'm doing it explicitly in equation 15 with the Taylor series. So I'm using the Taylor series definition, and it turns out that because the sz operator is diagonal, it is in fact possible to crunch it through analytically with a pencil. Then the bottom of equation 15 is the general solution. So psi t equals the exponential of the Hamiltonian psi 0. And from that general solution we can actually get all of the observables. And I guess I'll do that part on the board now. So psi t, as we discovered, is x minus I h t psi 0. H in our case is omega s z. If you follow through the handout, you will discover that this the exponential of this times t is in fact equal to this. So psi of t is, because Pauli matrices are 2 by 2 matrices, the corresponding Hamiltonian is also 2 by 2. The exponential of it is similarly 2 by 2. So it's e minus I omega t divided by 2, 0, 0, e I omega t divided by 2, psi naught. Well, depending on our initial condition, psi naught, we will have different answers for the dynamics. And, well, if we just put the initial direction, for example, along the z-axis, then psi 0 would be the same as spin up, yeah, alpha, which is in Pauli matrix notation 1, 0. If it's beta, it would be 0, 1. If it's in the transverse plane, it would be a linear combination of 1 and 0 with the appropriate coefficients. So, if we take a look, say we start along the z-axis and take a look at the various observables. So Sx will be psi of t, Sx operator, psi of t. The standard definition of the observable in quantum mechanics. Here you take the operator and you wrap it in the wave functions. Turns out it's 0. And if you look at Sy, that's also 0, and Sz is static and is equal to half. Not a very interesting solution. That's because we started with a spin that's already on the z-axis, and a spin that's on the z-axis in the z magnetic field doesn't evolve. It just stays there. And so the quantum mechanics told us that the projections on the x and the y remain 0, and the projection on the z remains equal to 1/2. Things get a bit more interesting if we start with a spin in the transverse plane. So if we start on the x-axis, then our initial wave function would be this 1/2, 1. So a linear combination of the spin up and the spin down, that if you compute these three expectations will correspond to Sx equals 1/2, Sy equals 0, and Sz equals 0, so it corresponds to a spin sitting on the x-axis. If we similarly take that vector, multiply it by this matrix, obtain psi t, then plug that psi t into here, do all the matrix vector computation, what we will get is something a bit more interesting. It will turn out that Sz is now equal to 0, and you know why. If the spin is in the transverse plane, it starts processing the transverse plane, the z component doesn't accumulate, unless there is relaxation in the system. But Schrodinger equation formalism doesn't accommodate relaxation well, so we shall just ignore it. And then Sx would be 1/2, yes, same magnitude, cosine omega t, and the Sy would be 1/2 sine omega t. Yeah, standard rotational dynamics, cosine projection, sine projection, that means spinning in the xy plane as a function of time. So, usual case of spin precession. And this is really how most of the simulations that you will ever do in practice will work. You will have your Hamiltonian, you will have your initial condition, which will either be a density matrix or a state vector, or in this case an actual wave function. You will be exponentiating that Hamiltonian, you will be multiplying it into the initial condition, you will be computing the observables. So all of the spin dynamics is fundamentally about this. There are various practicalities as to what the Hamiltonian is, in which cases, what it is that's permissible to ignore, what is the exact nature of the time dependence, but really all of that eventually boils down to this. And even the matrix calculations don't need to be done by hand, because if you just define one matrix and another matrix and tell MATLAB A times B, it will actually do a matrix multiplication. If you tell it to Mathematica, it will multiply matrices element by element. You will spend an hour figuring out what the hell is wrong until you realize that the matrix multiplication operation in Mathematica is denoted by a dot rather than a star. So take care, yeah, if you just use a star in Mathematica, it will multiply matrices element on element rather than the usual matrix multiplication. There we are. Okay, so this was the time domain formalism. Why don't we use the frequency domain formalism? And as you know, well, since lecture 1, time and frequency domain in magnetic resonance are related by a Fourier transform. So what we will now have to do is take the Fourier transform of the Schrodinger equation. Right. So back to d by dt psi of t equals minus I h. We'll do the time-independent variation because the frequency domain solutions only apply to time-independent Hamiltonians. Yeah, energy is only well defined if your time is infinite. Remember that certainty relation. So h will be static, psi of t. Well, let's do a Fourier transform on both sides. Because of causality, we cannot draw upon the system past, only the future. We assume that it has started at a particular point in time. And so it wouldn't be an integral from minus infinity to infinity. It would be an integral from 0 to infinity. Which is where the Hamiltonian was switched on. So, an integral from 0 to infinity of d by dt psi of t e minus I omega t dt. So, standard Fourier transform of that derivative. We'll do it with integration by parts. So, u is e minus I omega t, du minus I omega e minus I omega t dt. dv d by dt psi t dt. So v is just psi t. And that is then uv at the limits minus integral v du. What we get is this psi of t e minus I omega t, integral limits from 0 to infinity, plus I omega 0 to infinity psi of t e minus I omega t dt. What we will assume here is that when we have given the system an infinite amount of time, the wave function has spread itself across the universe, and its amplitude at any particular point is 0, and so the upper limit of that thing gets ignored, and so what we have in the end is I omega psi of omega. So this Fourier transform here, it's just a Fourier transform of the wave function, so called psi of omega, minus psi 0. Right, so that is the Fourier transform of the right-hand side, sorry, the left-hand side of the Schrodinger's equation. Fourier transform of the right-hand side is trivial, because the Hamiltonian is constant, so we just get that. So it must be equal to h minus IH psi omega. You see the great beauty of Fourier calculus. In action here, a differential equation in the time domain transforms into an algebraic equation in the frequency domain. The derivatives have disappeared. So we can actually solve for psi of omega. Psi of omega is equal, as a result, to minus I h plus omega minus 1, acting on psi 0. And we are adding a matrix to a number here. That's not a well-defined procedure. So what people typically do in these situations is they put a unit operator here. Get a unit matrix. And so now we are adding two matrices, and it's now well-defined. Okay, so in principle, if we would like to know the component of our observable, yes, so the Fourier transform of our observable at a particular frequency. So let's say the observable O at a frequency omega will be just the same thing. It will be psi of omega, O psi of omega, where psi of omega is equal to that. And this is an operator inverse, and in most cases it is well defined. However, there are situations where omega would hit upon exactly one of the eigenvalues of the Hamiltonian. So if omega is equal to minus the corresponding energy, the Hamiltonian eigenvalue of the difference would be 0. The inverse would not be well defined. And this is the primary weakness of the frequency domain formalism. It doesn't include relaxation. If we put a little bit of relaxation into here, so just a tiny bit of an anti-Hermitian term, I've called it IR, where R stands for sort of relaxation rate, then the singularity will be avoided in the complex plane, the inverse would exist, and there will be a certain amount of line drawing in the spectrum for this observable. So this could, for example, be the observable LZ. Yeah, LZ or LX, let's put it at the frequency omega, will be equal to that. And that's just a spectrum. So with the frequency domain formalism, you can solve directly for the NMR spectrum without ever propagating it in time or taking the Fourier transform, because you see, we took the Fourier transform at the very beginning. So instead of taking the Fourier transform of the FID, we have Fourier transformed the entire quantum mechanics, and of course it returns to Fourier transforms at the end. Right, so I've got another example in the handout of this time using the frequency domain formalism, and there are two ways of proceeding about it. One is formally exact, that is, if we just take this and plug it into here, what we will get is our observable, let's call it A of omega, will be that expression there, so I'll just plug it into there. Speaking of which, correct equation 22, it shouldn't be psi omega there, it should be psi 0. Psi 0, then H plus omega times the unit matrix minus R times the unit matrix minus 1, A H plus omega times unit matrix plus IR times the unit matrix minus 1, psi 0. So this could be computed with our damping rate R, and that would be the exact answer. We could try and expand this in Taylor series and use perturbation theory, that is to say, and if we do that, we eventually arrive at the second order accuracy expression known in the Trade's Fermi-Golden rule, where the probability of a transition per unit time between the initial state and the final state, depending on the frequency of the perturbation, is 2 pi h bar b fi, the so-called matrix element, times the density of the destination state, and that is 2 pi over h bar final wave function in the unperturbed Hamiltonian. Whatever perturbation we'll have usually would be the RF field, initial absolute squared times the density of the final state. A rather obscure thing, as you can see, that requires us to first solve the system for unperturbed states and decide what it is that we would have in the Hamiltonian, that's a perturbation, and then look at the transitions between energy levels under the perturbation. So best avoid it, as too many assumptions hidden in here, and really in situations with discrete and continuous spectrum there's also a lot of problems with the state density. So at least this is clear and understandable. So if you find yourself for some inexplicable reason using the frequency domain formalism, then that's the equation that you should be using. But really, for all practical intents and purposes, at least in modern NMR, frequency domain formalism is never actually used. It sort of survives on in textbooks, and it survives on in very simple undergraduate explanations which need energy levels. An energy level is a frequency domain phenomenon, well, notion. So please use time domain formalism, because there's just too many hidden pitfalls around here, like the necessity to introduce this complex damping term to avoid singularities and so on. So I don't think, except in teaching, I've ever actually used the frequency domain formalism ever. It has served its historical purpose. In our practical context, no longer necessary. But well, in the remaining time, let's take a look at a solution for a real-life two-spin system that can be obtained with the frequency domain formalism. Your equation 24, I wouldn't write it on the board because we are running out of time here. Equation 24 gives you a classical case of a two-spin system with Zeeman interactions on spin L and spin S, and also a J-coupling. Now, this J-coupling isn't an NMR J-coupling, otherwise I would have had to put a pi in front of it, but these are just operators, yeah? And you know what those operators are from the previous lectures, so for the time domain solution, what we'd have to do is simply put in those matrices, tell MATLAB to multiply them and add them together. We would have to compute the matrix exponential, multiply it into the initial condition, propagate it forward, look at the dynamics, Fourier transform it, we're done. In the frequency domain, what we do is we look, first of all, at the eigenvalues and eigenvectors of that Hamiltonian. So equation 25 deals with computing them, and then equations 27 and 28 actually list the analytical solutions for the eigenvalues and eigenvectors in terms of what is known in the literature as the mixing angle. That is very vaguely the ratio between the frequency separation of the two peaks and the coupling between them. And the picture at the bottom is what you get. You get 4 transitions in that system, and the transitions have got some intensity. However, you can see the line width is finite. That is because I've actually added a little bit of damping term in there to prevent the matrices from blowing up on the inverse. And so this line width is artificial, but the line positions and intensities reflect what we get from the quantum mechanics. So take a look through this if you are interested, but all of you sitting here, if you have to perform spin dynamics simulations, will always be doing them in that time domain. Frequency domain calculations are only useful for this textbook kind of examples. Okay, any questions?